Alright, what's up guys? In this video we're going to pick up with some partial differential equations, and we're going to be talking about harmonic functions and the two-dimensional Laplace equation. So we're asked to show that the following function is harmonic, that is, it satisfies the two-dimensional Laplace equation. So the two-dimensional Laplace equation is a partial differential equation. It's a second order equation, second order partial differential equation. And basically what we need to do here is show that the function is harmonic, which means that the function needs to satisfy the two-dimensional Laplace equation, which we know is going to be our second order PDE, which is equal to 0. So the 2D Laplace equation, let me remind you of what that is. You can write the Laplace equation in 3D as well, but in this case just 2D. So the Laplace equation, that's going to be del squared. Typically u is going to be used, but in this case the function that they give us is psi of x comma y is equal to e to the x multiplied by cosine of y. So in this case we'll just write it as del squared psi is equal to d squared psi over dx squared plus d squared psi over dy squared, and that's going to be equal to 0. So in the particular function that we're given is psi. There's also another way that these can be written. So to be del squared psi is equal to psi sub xx plus psi sub yy is equal to 0. That's the exact same thing, just written two different ways. So basically what we need to do is obtain the second order partial derivatives for this function with respect to both of the variables, which is x and y, and we got to plug them into the Laplace equation and see what happens. So typically, let me just do it over here just as a general. In our example, we're not given a function of u, we're given psi, but typically this is how it'll be written. It'd be del squared u is equal to d squared u over dx squared plus d squared u over dy squared is equal to 0. So it might be written that way. Okay, let's go ahead and obtain our partial derivatives. So we know we'll need to obtain the first ones, obviously, to get the second ones. So we'll start by finding the partial of psi with respect to x. So you just go up here to our function here, psi of x comma y. Well, if we're taking the partial with respect to x, that means we're treating y as a constant. Recall that the derivative, or the partial derivative in this case, of e to the x is just itself. So it would just be e to the x. And since we're treating y as a constant, the partial of psi with respect to x is just going to be e to the x multiplied by cosine y, or cosine of y. Doesn't change anything. You should also notice that when we find d squared psi over dx squared, you should easily be able to see that this is also going to be e to the x times cosine y, or cosine of y. Because again, here, recall that all d squared psi over dx squared is just the partial with respect to x of the partial, in this case, of psi with respect to x. Looks like my pen is going out here. That's all it is. So that's why d squared psi over dx squared is equal to e to the x times cosine of y. Again, we're partial differentiating with respect to x. derivative or partial derivative of e to the x is just e to the x. Again, we're treating y as a constant. So that's going to be our second order partial derivative for our variable x. Now we need to do it for y. So in this case, we need the partial of psi with respect to y. So again, we go up to our function here. Psi of x comma y, so we got e to the x times cosine of y. Okay, so in this case, we're treating x a constant. So since we're treating x a constant, we're going to take the partial derivative with respect to y for cosine of y, which is negative sine of y. But in this case, I can move the negative to the front. We're treating x as a constant, so it'll just be negative e to the x sine of y times sine of y. And again, we need d squared psi over dy squared. And in this case, again, all this is asking us for, or all d squared psi over dy squared is asking for, is the partial with respect to y of the partial of psi, and in this case, with respect to y. So these, if you remember from multivariable calculus, are just, hopefully you guys learned about mixed partial derivatives. You will have seen these different notations before. Okay, so let's go ahead and take our partial this time. So again, we're still treating x as a constant. So in this case, what will we get when we take the partial here? Well, again, we're treating x as a constant. So this would be negative e to the x. That doesn't change. And now we just take the partial with respect to y for sine of y, which you know is cosine of y. So we'll have cosine of y here when we take the partial. So now we have the second order partial derivative with respect to this variable, second order partial derivative with respect to that variable. And we need to substitute them into the two-dimensional Laplace equation. So if we go down here, you just simply have to plug it in. That's really all you have to do. And you look and see if it satisfies when you plug it in. So let's do that on the back here. All right, so we get d squared psi. So we'll plug in our second order partial derivatives. And so essentially what we'll have is e to the x times cosine of y minus, remember that the d squared psi over dy squared was minus e to the x times cosine of y. There was a plus sign in the Laplace equation formula, so this would just be minus e to the x cosine of y. And as you can clearly see here, this in fact does equal 0. And so basically what that means is that this function is in fact harmonic in this case. So that we can say that our function psi of x comma y is equal to e to the x multiplied by cosine of y is in fact harmonic because it satisfies the two-dimensional Laplace equation. That's pretty much how you do it. Okay, so if you guys got any questions about this, let me know. I'll be more than happy to explain it. But that's going to be it, and I will see you guys next time.